Hello everyone, I am Deepak and today we discuss about the topic of adhesion improvement of copper and copper epoxy joints. So in past few decades, silicon is most widely used semiconductor material for power devices and we attach the silicon die with tin based solders. But for high power applications, we use wide band gap semiconductor materials such as silicon carbide and gallium nitride. So, at the junction of wide band gap chips, the temperature may reach about 250 degrees centigrade, and at that temperature, the tin base solders may melt. So, to meet the need of high temperature electronic application, nanoparticle sinterings comes in picture. And basically, copper bondings have excellent electrical conductivity, high migration resistance, high thermal conductivity, and the low cost. But because of copper nanoparticles have easily prone to oxidize, which reduce the bond strength, reduce the electrical conductivity, and increase the bonding temperature. Similarly, we find some issues in copper epoxy bond also due to less surface roughness. The adhesion between the copper epoxy is too poor, and it results in failure in the device. So firstly we discuss about the copper bond. For formation of copper bond, we have to make first copper nanopaste, in which we take the nanoparticles, we wash it in acidic with the formic acid solution and centrifuge to remove its oxides which is present on the surface of the copper nanoparticles. Then we go to the drying process and then we mix it with some organic components and particles such as ethanol, ethylene glycol, DMAPD for making the copper paste. After making the copper paste, this is the actual procedure of making copper bonding, which is actually seen in the pictures. So in this, first we take the copper paste, we printed on it onto the copper substrate, and by using of the screen printing method, and put one more copper plate on it in the form of sandwich structure. After that, we preheated it at some temperature. Then we pressurized it in both from both sides and heated it at bonding temperature. And the heating temperature time is approximately 1 to 10 minutes. uh, After that, the bonding is takes place. So as we see in the figure, it is the actual the procedure of the making copper bonding.
Good morning to all. My name is Digvijay. Now I will discuss about factors affecting shear strength of copper bond. First, we have four parameters here. First, we will discuss about different sintering atmospheres. So when we use argon as our sintering atmosphere, you can see we get very less shear strength, about zero point 0.7 megapascal, and in air we get about uh, 5 megapascal, and when we use formic acid we get about 30 megapascal. So if we use platinum as catalyst with formic acid as sintering atmosphere, we get shear strength about 55 megapascals. Because the reason is, in platinum and formic acid we get high shear strength because there is formation of hydrogen radicals, and the oxide formation is very less, due to which we get high shear strength and clean surface. Okay. The second parameter is temperature. So as you can see in this in this figure 4 part B, that when we as we increase the temperature, the shear strength get increases. At 160 degrees we get the shear strength at about 12 megapascal, and at 220 degrees we get shear strength of about 25 megapascal. Beyond beyond 240 degrees we get our shear strength increases very fastly. It is about 55 megapascal. Why there is the shear strength increases very fastly, because the sintering kinetics increases uh, after 240 degrees, due to which copper and copper nanoparticles uh, cohesiveness increases, and the adhesive between copper and copper substrate also increases. The third parameter is but when we increase temperature more than 250 degrees, it is very harmful for our electronic devices, and it decreases our uh, thermal stability. So to compensate that, we increase our pressure. So you can see the third parameter, that is pressure. So when we increase the pressure from 5 megapascal to 10 megapascal, you can see that our strength at 5 megapascal is only 20 megapascal, but at 10 megapascal, by applying 10 megapascal pressure, we get the shear strength of 35 megapascal. But maximum pressure that we can apply is only 15 megapascal, because beyond 15 megapascal, if we increase the pressure, uh, our growth rate of nanoparticles will decrease. So we cannot increase the pressure more than 15 megapascals. Last parameter is our time. So in this figure, you can see that if we are doing sintering for 5 minutes, we will get the shear strength of about 45 megapascal, and if we are doing sintering for about 30 minutes, we will get 52 or 53 megapascals. So there is not much difference between the shear strength. So you can see we can do rapid sintering at low temperatures for copper copper bond. This was whole about when we are using nanoparticles. Now now we will discuss uh, when when uh, when we use microparticles plus nanoparticles copper composite paste for bonding copper copper for bonding copper copper. So in this we have used microparticles. You can see this black part is microparticles, and we have sprinkled nanoparticles on them. So at the time of reactions, these microparticles are uh, nucleating sites for nanoparticles. You can see that these nanoparticles are growing. These are growing at the time of reactions, and after that they both get mixed. Both get mixed, nanoparticles and microparticles. So we in this we have taken uh, 5 ratios of nanoparticles and microparticles, and have studied about uh, shear strength and porosity and resistivity. As you know that as the resistivity of the bond between the bonds decreases, the resistance decreases, and we get good electrical conductivity. And when the porosity between the bonds decreases, we get better thermal conductivity and better heat dissipation. So as you can see, these are the 5 mass ratios that we have taken, like 2:1. Here the ratio is between nanoparticles to microparticles. So 2:1, 3:2, 1:1, 2:3, and 1:2. As you can see that when we have decreased our mass ratio from 2:1 to 3:2, our porosity and resistivity both get decreased, and we get both good thermal conductivity and good electrical conductivity at this ratio. But beyond this, but when we decrease this ratio to 1:1, our resistivity and porosity gets increased again. So it is better to keep the ratio from 3:2. The other factor that we will discuss is about shear strength. You can see that when the ratio is 2:1, our shear strength is 46 megapascal. When we decrease the ratio from 2:1 to 3:2, our shear strength get decreased to 44 megapascal. There is very less change in shear strength. So we can use 3:2 mass ratio. But if we further reduce our mass ratio to 1:1, there is very huge change in shear strength. It has decreased to 35 megapascal. This is because the void formation between nanoparticles and microparticles of copper are more, due to which the shear strength can decreased. So now my friend Prakash will discuss about copper epoxy bond.
Hello everyone, my name is Prakash Kumar and I am going to discuss about the copper epoxy bonding. So copper epoxy bonding is done by the adhesion process. So improving the interfacial adhesion between the metal or copper substrate and the epoxy is very important for the uh, reliable electronic devices, because if the proper strength of the adhesion is not there, then this may cause the delamination. Delamination, which means the separation of the copper and the epoxy uh, copper and epoxy resin. So this causes the failure of the electronics devices. So there are copper substrate, which is metals made of a metallic object having a two type of surface roughness. One is the higher surface roughness, other is the lower surface roughness. Generally in higher surface roughness is the adhesion is done by the mechanical interlocking between the copper and the epoxy. But in low surface roughness, having a surface roughness is 0.1 micrometer, so there is a less surface roughness, so mechanical interlocking is not significantly possible. So we introduce one UV or ozone method, uh, which is used for increasing the adhesion strength between the copper and epoxy. So UV method does not damage the substrate also, because surface roughness is not changing significantly. Now this is the procedure of the ultraviolet or ozone treatment with the copper substrate. The in this method, copper metal were exposed to the UV light with a wavelength of 185 nanometer and 257 nanometer, in which when the UV light is exposed at the surface of the copper substrate, copper is oxidized to the copper oxide and the copper hydroxide, which can be seen from these two graphs. Like this is showing the intensity and the binding energy of the copper oxide and the copper hydroxide, in which let's say at 0 minute, when the ultraviolet light is not exposed to the surface of the copper, there is a binding energy of 567.4 electron volt. As we increasing the timing of the ultraviolet light on the surface of the copper, the binding energy peak is shifting to the some higher value, which is 568.7 electron volt for the copper oxide. The same case is also for the copper hydroxide at the initial at 0 time, which is a 932 electron volt. As we increasing the intensity of the ultraviolet exposure time to the surface of the copper substrate, the binding energy is shifted to the some higher value, like 935.2 electron volt. So after that, when ultraviolet region is treated to the copper substrate and formation of copper to copper oxide and copper hydroxide, then then after that, saline coupling agent, which is adhesion promoter, was applied to the ultraviolet or ozone treated copper, which is ensures the uniform coating, which is shown in the figure. Then after that, epoxy is molded with the hardener, which is in the weight ratio 4:1, and this mixture was applied to the saline coated copper substrate and then cured using a hot press at 120 degrees Celsius and 7.5 megapascal for 30 minutes to form a solid epoxy layer, which is shown in the last figure of this procedure. These are the result and discussion, which is shown by the graph. First is a peel strength with different copper substrate. Like first in figure A, which is shown is the bare copper substrate, in which there is no any UV light is implemented. Second is only UV light implemented. Third one, and in this graph, there is the highest peel strength. Peel strength is a amount of force which is required to peel the surface of a epoxy from the copper substrate. So in this case, in the case number D, which is higher, because in this method UV light is implemented along with the saline along with the saline coupling agent is implemented. So in this method the peel strength is 1.85 kgf per centimeter, which is 1.9 times higher as compared to the bare copper. After that, in this figure, which is APTMS, APTMS and TPDA, these are the saline coupling agent, which is showing the variation of different coupling agent with the peel strength. So in this graph, the TPDA, which is a saline coupling agent, which is highest peel strength as compared to all, because it is having some hydroxyl group which promotes the better bonding between the copper and epoxy layer. And now the figure 13 shows the peel strength variation with the UV exposure time, which is shown as the UV exposure time increases, like 5 to 10 minutes, 10 to 15 minutes, and up to 30 minutes, the peel strength is also increases, because when the UV exposure light times is increasing, the copper is more oxidized to copper and copper oxide and copper hydroxide, which forms a greater bond between the copper and the epoxy, copper substrate and the epoxy. So that's why the peel strength is increasing as the time of this exposure time is increasing. Now these are the future trends for the copper epoxy bonding, like determining the best exposure time of the UV or ozone to enhance the adhesion without excess and oxidation. Because as we increasing the time, suppose that copper is oxidized to copper oxide and copper hydroxide, so we can do that at a optimum time. What is the optimum exposure time, so that the excessive strength or the adhesion strength is maximum. Exploring a new saline compound for stronger and more durable metal polymer bonding, and implementing this adhesion enhancement technique in flexible electronic, like some other different electronic components like PCB or larger electronic components and microelectronics components. Thank you.